Welcome on the afternoon session. So we have 6 talks. I will be showing the first 3, and Professor Marian Józek will be sharing 3 talks. And it is my great pleasure here to have Mateusz Przybylski, my scientific brother, my brother. And Mateusz will be speaking about the topological methods in dynamics reconstructed from biases.
Thank you for the introduction. I want to say thank you to the all organizers for giving this talk. I'm going to talk about the topological methods, or in fact, one topological method, namely the common index theory, in analysis of data-driven dynamics. I will start to the dynamics reconstructed from the time series, but also our method can be, after a little modification, adjusted to analyze dynamics given by sampled map. I mean, the argument in the value. This is joint work with Marian, Bogdan Barko, and Konstantin Szajkov. Okay, and I want to give you a quick guided tour through the whole pipeline, how to use this method to the setting of time, in the setting of time series. I'm very lucky because Niklas and Justyna today's morning gave a talk, and they introduced the first step of our method, namely the Takens embedding theorem. So I guess that all of you are know everything about this method. I just recall quickly. We start with the time series, the sequence of real numbers, and we need to fix a set of parameters. The first parameter is the dimension of embedding space. About the fixing a set of parameters, this is another project. This is another issue. We just did a kind of grid search for the dimension and the cube. The next parameter here is the lag of the shift map. We fix this lag equal to 1. Then we build the set of points. We take the consecutive elements from the time series, and the next the consecutive elements, and so forth and so on. Then we build the shift map, which maps, as in this example on the figure, if we fix embedding dimension equal to 2, then we map 2 first elements to another 2, and so on. And this is exactly the same example Niklas showed us today. This is classical example with the time series generated from a sine function with some random noise here. And after the reconstruction, you see on the right that we have ellipse-like shape, which shows us kind of periodic behavior. So we expect that after the reconstruction, we get a kind of something which mimics the dynamics given by original but unknown dynamical system which generated the time series. And this is a quick recap on Takens embedding theorem. We do not know the manifold. We do not know the embedding this dimension of the manifold. We also don't know the original dynamics, this phi map here. We only know the measures, numbers we reconstructed given by this set. And the Takens theorem claims that, that there exists, in fact, topological conjugacy, of course, on its image. And we have this conjugacy equation here. Conjugacy between unknown map and this shift map. Okay, so That was the first step. We have time series, then we create this shift map, and now we go to the part of Conway index theory. So we need to reconstruct somehow multi-valued map. And there is a classical way of do that. We have to fix a third parameter, namely the size of the cube, because we want to cover whole space with cubes. And we build multi-valued map as follows. We look for all points in one cube, then we take the values of shift map of those points and cover them by cubes. And here is the first major obstacle. We need to have acyclic values of this multi-valued map. This is because of algebraic topology under the index theory. And the easiest way to ensure that the multi-valued map has a cyclic value is just to take the smallest rectangle or smallest cuboid. This is, of course, convex, so contractible, and it implies that it is acyclic. But there's a problem with overestimation. As you can see on that figure here, that, yeah, we added a lot of cubes here. And if we add a lot of cubes, then we probably lose nice dynamical phenomena from our map. So we need to find better values for the multi-valued map. And the other idea was to take those values of shift map, take the convex hull of those points, and then cover this convex hull with cubes. And as you can see here, the value is smaller, significantly smaller than the value of this cubical enclosure here. And of course, we showed that this value is also acyclic, it's contractible, so also acyclic. So the proposition here give us most important features of those two multi-valued maps, namely they both are upper semi-continuous. This is kind of continuity for multi-valued maps. Both are cubical. That means that the map is constant on combinatorial interior of the cube, and the value is the union of cubes. And the most important for us, both maps have contractible values. Maybe I just comment here that in application, if you try to build multi-valued map, then it is almost sure that your value will be, as on that example, will be, for example, disconnected, or there is no chance for acyclicity for any value in applications. So this step is very important here. Okay, so now let's go to the index theory. Our result is from the recent Conley theory for multi-valued maps by Marian and Bogdan Batko. It works on the slightly relaxed definition of isolating neighborhood and a weak index pair. This is very nice feature because it is much easier to find computationally those objects, isolating neighborhoods and weak index pairs. And moreover, in this recent theory, the isolating neighborhood is defined in classical way. This is exactly the same condition as in the classical approach. Invariant part of the set is included in the interior of the set. Invariant part, as Marian said yesterday, if you think about the multi-valued map as directed graph, then if there is a B-infinite path in this graph, then it means that all that points from that path are in the invariant part of subset. This new theory also allows us to find quite easily weak index pair, especially if we find the special class of isolating neighborhood, namely the isolating block. As you can see here, this is very easy condition to check algorithmically. Namely, here we have only intersection of some sets, so this is quite easy to check on computer. And if we find the isolating block, then we can build the weak index pair. This is an auxiliary notion. I do not go into the details. You can look for the references to see more details in that. Okay. There is another abstract rule if you want to apply our method. Namely, the previous approaches demanded from us the existence of continuous selector. What is the continuous selector? This is continuous map, which graph lies in the graph of the multi-valued map. This is because the algebraic topology under the Conway theory, because we want to induce map in homology, and this continuous selector ensures that we can do that. But as I mentioned, it may be very difficult to find a continuous selector, and moreover, in application, it is almost impossible to find, if you reconstruct multi-valued map, to find the continuous selector for this map. This is more example which you can encounter when you look for the multi-valued maps generated from the data. So you have this acyclicity here, but there is no chance to put continuous selector to this map. So we are interested in so-called epsilon approximation. The continuous map, which are epsilon close to the, which graph is epsilon close to the graph of the multi-valued map. And this allows us to build a bridge from this combinatorial dynamics to the classical single-valued continuous dynamics. In our pipeline, we want to find the lower bound for the complexity of the system. In fact, in our experiments, I will show you in a moment, we show that the systems are in fact chaotic, are very complex. In order to do that, we need to compare the complexity of the dynamics to well-known dynamics. And by this well-known dynamics, I mean the symbolic dynamics, sheet dynamics. So let's pick the finite set of symbols, and let A be a matrix of 0, 1 entries with 0, 1 entries. We call some map A admissible if it obeys this matrix. I mean, if we have, on this example, if we have the B infinite sequence 2, 1, 3, 2, 1, 3, and so on, that's okay, it's A admissible. But the second one is not A admissible because there is double twos here, and this is not allowed because we do not have in the second row and the second column of this matrix 1. So this is not A admissible here. And if we consider all the infinite sequences, the set of A admissible sequences are subspace of the whole space of these B infinite sequences. And moreover, we can introduce here a shift map, which shifts the symbol of one position. And this is a homeomorphism, and we have this invariance here for the subspace of A admissible sequences. So this was quick recall on symbolic dynamics. And let's go to the results. What we can get, we have two kinds of results. The first was the numerical experiment, the second was the physical experiment. The numerical experiment, we take the human map. It is well known, we know that it is chaotic for some set of parameters. We fix the parameters like that. This is not the standard parameters for the Hinon, but those parameters are from the region where the Hinon is also chaotic. So we tried with different parameters and it works in all cases. And then we started from the point 0, 0 and iterated this Hinon map and only take the first coordinate and build the time series from this first coordinate of the iterates of the Hinon. We fixed embedding dimensions equal to 2. So size of the cube for the overgrid. And we needed about 24,000 elements in time series. And we get the result like that. Okay, from this time series, we can build the first sheet map. Then we can build the sunflower enclosure. This is better version of the multi-valued map with smaller values. And we know that for every epsilon from the interval 0 to delta half, delta is the size of the cube, we know that the set of epsilon approximation is not non-empty. So there exists some single-valued continuous map which are epsilon close to the our multi-valued map. Moreover, we found the isolated neighborhood for our sunflower enclosure multi-valued map. And this isolated neighborhood coincides with the isolated neighborhood for all epsilon approximation. And moreover, there is semi-conjugacy from the subset of invariant set for epsilon approximation, for every epsilon approximation, to the subshift of finite type on 8 symbols here. What does it mean? This semi-conjugacy gives us the lower bound, because if we have the semi-conjugacy, if we apply the topological entropy, this is quite easy to find the topological entropy for the symbolic subshifts, because this is spectral radius of this matrix. And we found that, in fact, the topological entropy for every epsilon approximation is positive. That means that the dynamic behavior of epsilon approximation is very complex, is chaotic. And here are the attractor of Hinon. Here we have the decomposition of isolated neighborhood onto some numbers of components. There is the weak index pair, but maybe this directed graph is important because it shows the transitions between components. Okay, so we wanted to check if the Takens theorem is true. And we increased the embedding dimension, and we expected to get the result again about the complex behavior of all epsilon approximation. And this is exactly the same theorem as before. But of course, the transition matrix is slightly different because we get slightly different isolated neighborhood for this multi-valued map. And here are the attractor for Hinon, three-dimensional Hinon map, isolated neighborhood, and the transition between components of isolated neighborhood. In order to show that the Hinon two-dimensional or this delayed three-dimensional Hinon generate chaotical multi-valued map, we needed time series of length over 20,000 points. We needed those numbers on average because we also, for some parameters, were able to find the same result, but for the shorter sequence of length 8,000 points. But in average, we needed 20,000 points to show this kind of behavior. Okay, we also have a result for physical experiment, namely the magnetoelastic ribbon. I will describe you, but if you have some question about the details, please look to the references. So I am not sure if I understand correctly what they did. But magnetoelastic ribbon is kind of strip of metal which Young modulus is changing in varying magnetic field. Young modulus is responsible for the stiffness of the material. So if the magnetic field is changing, then the stiffness is changing, and this strip of metal bent back left and right. And those displacements were measured, and they got time series of length 100,000 points numbers. So we fix dimension 2, the size of the box, size of the cube, and we get again the same kind of result, of course, with other transition matrix here. And here is the attractor for this magnetoelastic ribbon. Isolating neighborhood and the transition between components of isolating neighborhood. And again, we check it for increased embedding dimension, and we again got this kind of result as here with another transition matrix. And okay, you can say that this looks like a kind of applied mathematics, but applied in pure mathematics, because we can tell something about the complexity of some system. But we also did some using exactly the same pipeline and procedure as I presented you. We can also claim about the existence of periodic orbits. And for example, for two-dimensional Hinton map, we showed rigorously that there exists non-empty class of epsilon approximation with two periodic orbits. And in order to show it, we needed only 286 points in time series. Rigorous result. Okay, here are references. Thank you very much.